Good afternoon to all. My name is Shuman Devnath. I'm working as a PhD scholar in Department of Electronics and Communication Engineering at Tripura University. Today I'm going to give my presentation on my topic. It is ML-based modulation format identifier using Canon algorithm. The authors of this paper are Shuman Devnath, Nidhi Sinha, and Dr. Bishankar Ratta Bhoumi. My presentation contains these following outlines. First, introduction, then methodology, then Canon algorithm, then training samples generation, analysis of patterns, and finally the conclusion. So in advanced modulation format, in today's era of communication network in the field of mobile voice, internet access, streaming, broadcasting, and various data services carried on across the globe that relies on ultra-fast broadband solution capable of providing high-capacity data networking through optical fiber communication systems. The need towards increased per fiber transport capacity as well as the goal for reduced cost per end-to-end transmitted data bit has resulted in optically routed systems with higher spectral efficiency. Various communication technologies are being used for proper utilization of the bandwidth demand for various application purposes in a most cost-effective manner. Advanced optical modulation formats, among other supporting technologies, has proved itself as one of the most critical aspects in the design of modern fiber communication system. Advanced modulation formats are seen as a promising direction to enable long-distance transmission for high-speed data. Modulation format is one of the key adaptive parameters in feature elastic and cognitive optical networks, which means that the modulation format at the receiver side is likely various at different moments. Therefore, the real-time information about modulation formats of received signals obtained through a modulation format identifier can enable the receiver to adapt algorithms most appropriate for these format types to achieve the optimum performance. So ML is an area of artificial intelligence or AI that refers to computational algorithms that rely on prior knowledge to improve performance or generate precise predictions. Optical communication networks are getting increasingly more complex due to the fast development both in terms of services and technologies, especially with the introduction of complex modulation formats. In this context, enabling the deployment of next generation autonomous optical networks capable of conducting modulation format identification to correctly detect and identify the type of modulated signal at the receiver end is a frequent necessity. By implementing intelligent system based on machine learning technique, it is possible to incorporate intelligence into communications networks in order to overcome the significant problems of system complexity and the need for manual operation. This is the proposed block diagram of the model. Here we are sending BPSK, QPSK, 8PSK and 16PSK signal through the single mode fiber, and after this there is an EDFA, an amplifier, and after this we added an optical detector to detect the signal, and then coherent receiver is there to receive the signal. After the coherent receiver, the constellation plot of the incoming signal is generated, and this constellation plot is actually compared by using a Canon approach with the training data previously stored, and hence the level detection is calculated to find the perfect modulation format of the incoming signal. The KNN algorithm, actually the KNN stands for K nearest neighbor algorithm, is a popular technique used for predictions. The whole training data set is used to represent the KNN model. Here the training data is stored first with which will make it easier for searching for new patterns during predictions. The algorithm predicts the new data point to be the nearest neighbor based on the closest data point that is available in the training data set. A distance measure is generally used to identify which of the k instances in a training dataset is most similar to the newly entered dataset. In the case of real valued input variables, Euclidean distance measure is mostly used. The Euclidean distance is calculated by summing all the square differences between a point x and point y, and finally doing the square root of the summarization value across all input variables. That is shown is here through the equation given in the PPT. The value of k can be found by tuning the algorithm that determines the most similar neighbor or the last Euclidean distances measured to the new data instance. The training samples that are samples generated from the constellation points. So the constellation points of the BPSK signal and QPSK signal are converted into the training data samples, and accordingly the 8 PSK and the 16 PSK signals are also converted into the samples, and which are stored here as the data samples. The data samples here are first identified as the modulation format. If it is the BPSK, then the level is given as 2, and all the pixel values uh, are stored in a particular row. The second row, we can see it is the QPSK and the level is 4. And accordingly, 8 PSK, it will be the level 8, and 16 PSK, it will be level 16. So accordingly, all the pixel values are stored in the particular row formats. And here we can store about 1,000 or 10 or 5,000 of the total pixel values to make it more precise for the detection of the incoming signal. So in the analysis of the pattern, we already have the tested, that is a training data sample, and we have the incoming signal. So the incoming signal is first converted into the constellation plot, and the constellation plot data of the incoming signal will be compared with the already stored training data samples, and both the samples will be compared by using the KNN algorithm. The KNN algorithm actually finds the sample points of the training data set which are closest to the incoming signal constellation and are selected, and the final output is chosen based on the number of occurrences of the level defined in the training sample. So in the conclusion, we can say that we have successfully incorporated the intelligence into our optical communication networks. The proposed technique employs the KNN algorithm to identify the modulation format of the incoming signal at the receiver end. And we successfully able to detect 4 PSK signal, and these are the BPSK, QPSK, 8 PSK, and 16 PSK respectively. These are my references. Thank you to all.